It's easy to take our world for granted. Every day we see a blue sky and blue ocean stretching out to the horizon. But from a planetary perspective, these aren't the most common colors. And nowhere is this clearer than when you look at distant exoplanets. But what makes our planet so blue? Does it have to be this way? Will our oceans always be blue? Welcome to my channel. In a new paper in Nature, Japanese researchers have made a compelling case that Earth's oceans were once green instead of blue. Oceans make up nearly 3/4 of Earth, so the color of our oceans dominates how the planet looks from space. Most people think of the oceans as blue, but a closer inspection reveals a more subtle range of colors. It's a cobalt blue in the deep sea where sunlight doesn't penetrate and the water molecules are pure. Closer to shore, the water can appear turquoise, azure, teal, or aquamarine, depending on the depth and the angle of the sunlight. It can even reflect the colors of the bottom or the sky. Sometimes it appears almost black when the surface is calm and the water absorbs almost all the sunlight. But other times it can be emerald green, especially in shallow waters or when there's lots of phytoplankton in the water. But before considering how our oceans might change in the future, let's consider why they're blue in the first place. Water itself doesn't absorb visible red light. Instead, it's scattered by water molecules. Visible light has wavelengths of roughly 400 to 700 nanometers. Water molecules absorb light longer than 700 nanometers, which is in the infrared. This means that if sunlight hits water molecules, they'll either bounce away or get absorbed and re-emitted as infrared radiation. If the radiation re-emitted from the water is in the visible spectrum, we see this as blue light. In deep water, where the light's had time to lose its red wavelengths through absorption, this explains why we see cobalt blue. Near the shore, where the water is shallower and light hasn't had time to lose its red wavelengths, it can reflect the red, orange, and yellow of the sand or sediment. Similarly, in clear water, we sometimes see the sky reflected in the ocean surface. Even phytoplankton play a role in changing the ocean's color. They're green, and so they reflect green light, so the color of the ocean depends on its location and composition. But just how blue is our ocean? To answer this question, we need to go back in time. Nearly 3/4 of Earth is covered by oceans, making the planet look like a pale blue dot from space. But in the 1960s, Mariner 4, the first spacecraft to successfully reach Mars, sent back photos of the red planet that showed a pale blue haze obscuring the planet's surface. Was the iconic blue ocean now an artifact of human imagination? Today, scientists agree that Mars is covered in a thin layer of carbon dioxide ice and dust that scatters sunlight and gives the planet its blue appearance. So the Mariner 4 photographs didn't show a watery ocean. It did, however, spark a debate. Are our own oceans really blue? In reality, Earth's ocean is a complex mix of water, dissolved minerals, gases, organic matter, and particles. The exact shade of blue depends on factors like the depth of the water, the angle of the sun, and the amount of suspended particles. The wavelength of light and the path it takes through the water determines whether it's absorbed, scattered, or transmitted. Particles suspended in the water tend to scatter light, often making the water look greener. Even phytoplankton and other microscopic marine plants absorb sunlight for photosynthesis and scatter blue light. So our oceans appear blue. However, this effect isn't nearly as strong as in a pure water sample. When the concentration of phytoplankton increases, as in the summer months, the ocean can take on a greenish tinge. So in truth, our oceans are more of an aquamarine than blue. The question of whether our oceans will always be blue is more difficult to answer. It depends on how we define always. Over millions of years, the chemical composition of the ocean has changed and will continue to change. For example, in the late Archean eon, Earth's atmosphere and ocean were devoid of gaseous oxygen. Early photosynthesis by single-cell organisms caused the accumulation of oxygen in the oceans and atmosphere, triggering the Great Oxidation Event and making complex life on Earth possible. This also turned the ocean blue. Since the oceans are part of the rock-water atmosphere system on Earth, the processes that formed them are connected. Changes in one sphere affect the others. So as the oceans change, so will the color. So unless you believe that our current form of life will never evolve or change the planet, our oceans won't always be blue. In fact, some parts of our oceans already appear green. In the 1960s, Mariner 4 showed us that Mars could look blue. Since then, satellites have shown us that Neptune and Uranus look blue. Could a similar process be happening on exoplanets, giving them a blue appearance due to atmospheric gases? Some gases like methane absorb red light and reflect blue, like our oceans. But if the pressure and temperature of a planet are different from Earth's, the gases will absorb and reflect different parts of the visible spectrum. The color of exoplanet atmospheres can tell us what gases are present. This helps astronomers identify planets that could harbor life. However, it's worth remembering that the shades of blue we see on other planets aren't the same as our oceans. The gases that cause these blues are quite different from the water and phytoplankton in our oceans, so it's unlikely that aliens looking at our planet would see it as blue. Instead, they'd see a murky green soup with little signs of life. I'm a Cambridge PhD student and science communicator. Thanks for watching this video.